Okay, so today or now we're going to talk about dimensionality reduction. And so maybe since I already mentioned that these slides are by Max, there is no Max slides without some funny gifs, right? So we got that out of the way. But so why do we actually care about needing dimensionality reduction, right? So of course you most likely have heard by now already about such a thing as the curse of dimensionality, right? So there is actually like different aspects of it. Some of it is related to basically modeling probabilities or distances around high dimensional spaces. So those are like a big issue, but that's not actually what we want to talk about today. Today, we want to talk about rather making sense out of high dimensional data and making sense out of the data by projecting it into a low dimensional data that we can easier parse and interpret, right? So hence, like the context to explainability. So in case you're not familiar with the data source, the idea here is that basically all of those point distributions, right, actually have the same statistics, which like the deviating third point after the comma or something like this, right? Even though that the actual representation is very different, like all of the usual statistical values are very much the same. And that shows you that just looking at statistics by itself is not sufficient, right? Yeah, and same might be true in the case of deep learning, or is true in the case of deep learning. So even our latent spaces in the generative models that we talked about before, right, they're still fairly high dimensional. But if we want to analyze them a little bit, it might make sense to project them down into a lower dimensional space that we actually can then, as humans, make sense of. So for some examples, for instance, like ResNets still have like a 2048 dimensional space, right, like a ResNet 50. But even Stable Diffusion has 64 times 64 times 4, right? So like this is still like even the four-dimensional one is still like can be complicated for certain aspects, right? Because thinking in four dimensions for us is not as intuitive, right? There's another slight motivation here. So, and that is that if you actually like once you actually familiarize yourself a little bit, right? So with like looking and analyzing data, very often like this is an XKCD comic in this case, right? So you might actually do the statistics as we showed before. However, they might not be as like interpretable or as meaningful as you might guess, right? And once you're a bit more advanced and you have a good dimensionality reduction, you basically just look at the data and you get an idea, right? If there's something off or like if there's something that makes sense or not, that does not make sense, right? So dimensionality reduction, even if you don't really care too much about explainability, but if you want to see like, okay, is there like a bug in my code or like is there something like weird happening in the latent space that shouldn't happen or in any high dimensional space really, like it is good to know these techniques, right? In particular, we're going to briefly talk about three of them in chronological order. We're going to start with PCA. Quick show of hands, how many of you know PCA already? Yeah, that's what I figured. So we're going to do like the bare minimum of PCA, right? Then we're going to talk about TSNE. So how many of you know about TSNE? Okay, that's significantly fewer. And how many of you know about UMAP? Okay, that's barely anyone. Cool. I mean, you're still someone, right? But like, not as many. So let's start with PCE. I think everybody knows this kind of motivation, right? So if we actually have correlated data and we kind of want to project it more into, let's say, a lower dimensional space, or rather, if we actually want to decorrelate it, right? Because that's kind of where PCA originally came from. So the idea that to identify, instead of the given axes, identify a coordinate system where basically those different data points become uncorrelated in the sense that you figure out like which one seems to be the one with the most spread, right? Like where's the most variety here happening. So again, so if we actually project it first on the U line, right, then we can see that afterwards there's barely anything left for the V dimension to learn or to match, right? And in this case, U and V would be what we refer to as principal components. So the statistics view, there's different views, right? There's like more visual views and so on, but I think the statistics view is the one that we all are familiar with, right? So if we actually look at the covariance of our data, right, we can then use this characteristic polynomial in order to compute the so-called eigenvalues. And the eigenvalues basically tell us the magnitude of our principal components, right? So saying that the higher the eigenvalue, the more spread there is along this, like, or the corresponding axis. And the corresponding axis is what we usually refer to as the eigenvectors, right? So, and the eigenvectors we can then find basically by solving this equation down here. Of course, since the vector or the eigenvector is a directional indicator, right, and the eigenvalue is basically the magnitude of that, right? So it makes sense that it's normalized to 1, right? So I understand this was all very fast, but again, I don't want to spend too much time on PCA because everybody knows it already, right? Yeah. Any questions about that so far? Okay, then finally, actually the PCA transformation is reversible, which is really, really neat, meaning that if we actually can, if we go all the way and identify all our components, right, we can recorrelate our data again, right? So, and this becomes actually quite interesting in many ways. So imagine, for instance, right now, some of our current research that we'll talk about tomorrow afternoon is about like the tokenization of trajectories, right, in order to generate behavior. And one of the big issues that we have there, if we actually produce our tokens and we don't want to produce them in an autoregressive way, but in a parallel way, we don't maintain the correlation anymore, right? Which is really stupid. But what we can do instead is, if we first project it into this uncorrelated space, we don't need to maintain a correlation anymore. We just need to remember what the actual transformation originally was, right? And then we can, or the directions of the components, and then we can recorrelate it afterwards, right? So then basically meaning the actual production of the tokens doesn't have to be correlated anymore, right? So that's like super, super neat. Yeah. So, and like, I think one of the most famous examples of eigenvectors or like of PCA would be the eigenfaces, right? Where each of those like dimensions here or like axes here represents a different eigenvector, right? And then by weighing how much we care about the individual ones, we can potentially reconstruct, but also kind of learn what identifies a person, right? And if we then want to identify the person again, we can do this by leveraging those principal components as feature embeddings, right? So, and I think that is PCA in a nutshell. Any questions about PCA? No, super boring. Heard everything already 20,000 times, right? Sure. So let's go.
What is the diagram doing on the left?
Say this again.
Yeah, what is the diagram on the left?
Oh, that basically would, oh, sorry. That's the visualization of the iris data set. That's a very common, like.
Yeah, but how does it relate to PCA?
So iris data set is high dimensional, and you basically break it down into like the two most principal components and plot them. And that allows you now to identify 3 clusters.
Yeah.
Excellent point. Sorry, I should have been clear about this. I just wanted to get proof PCA because, again, fairly boring, right? Not boring. Amazing work. We owe it a lot, but I feel like everybody has heard about PCA like 20,000 times already. So it's just important that we mention it. So that's why we did it. And to this day, it's actually still used quite a bit, right? So, but since 2008, there is a new contender for like at least in terms of visualizations, right? And that would be TSNE, right? So let's talk about TSNE a little bit. So in contrast to PCA, TSNE is considered like a graph-based projection, right? Or a graph-based visualization. So what does that actually mean? So again, like this should pop up one after the other. So don't try to read all of it at the same time. We're going to go step by step through it, right? So imagine if we now, for instance, have our our dots in some high dimensional space, right? So here visualized in 2 dimensions and so on. They are somewhat like they have different distances to each other, right? Whatever this distance may be, that at this point doesn't really matter. In this high dimensional space, they are not all at the same point, right? That makes sense, right? So the question now is, how can we basically group those or find others that are similar to each point, right? So like each of them wants to identify, so we want to kind of make sense of this local structure, right? Local structure basically meaning like, hey, what are other points that are similar to myself, right? Those are my local neighborhood. And what are points that are different than myself? Those basically are like should be away, and those are like should be respected on a global structure, right? So TSNE or SNE in general is really good with respect to maintaining this local structure, right? And kind of falls down in the global structure, which we'll talk about in a second. But so how do we actually measure what is ours, right? We do this through this overall Gaussian distribution, right? So like imagine here, those are two unnormalized Gaussians, right? And our point of interest in this case would be J. Oh, sorry, would be actually I would be our point of interest, right? So we want to see what is the probability. So this actually should be like the probability of xi given xj given xi, right? So this probability, what is the probability for the data point xj being similar to xi, right? And as you can imagine, since this is basically just a unnormalized Gaussian, this is like a sphere, right? So it basically spans a sphere around itself. Like in 2 dimensions, it looks like an ellipse. Do we have something like this? In 2 dimensions, it would look like an ellipse, right? In 3 dimensions, like a sphere, and so on, right? So because we have here basically the L2 norm or the Mahalanobis distance, where the point itself serves as the mean, right? And then we have this standard deviation, or like the variance in this case, sigma I squared still, right? And the only thing missing is the normalization constant. And the normalization constant comes in through the denominator term, right? Where we basically say like every other point, right? So like what is the probability of the point J being similar to myself, so to I, right? Weighed against all the other points, being similar to all the other points, right? Does it make sense? So this is overall still a true, oh, you cannot see the cursor. So this at the end is still a true probability, right? This is still a true probability, like summing up to 1 and so on, but it's a conditional probability, right? That's also why you might be confused to say like, oh, wait a second, Rudy, like I know my math, right? And like if you actually have the normalization constant, it has to go over all the data points, including itself, right? And here it says k without I, right? And that's because it's a conditional probability, right? So conditioned on I. So that's why we don't consider I itself here. Okay, cool, excellent. So with this, we basically get like this kind of like this measure of locality or like the similarity measure in SNE. Now the question is, how do we actually get our sigma I? And this is something, oh, here, our sigma I, right? Because we already established that xi or in this case would be the mean, right? And so how do we get like the sigma I part here? That is through something that we call perplexity that we'll talk about in a second, right? So it's something like the number of neighbors, but not quite. Okay. So we do this in a high dimensional space, okay? So in the low dimensional space, we actually just like not going to use any sigma, right? So we're going to drop it off. So this would be equivalent to using the standard deviation of 1 divided by 2. So we don't have the 2 in the denominator anymore, and the sigma itself basically disappears. So we're just going to use something. So now if we have now, for instance, let's say a 2-dimensional space or something like this, right? Or a 3-dimensional space or whatever dimensionality we want for our lower dimensional representation, right? We use this loss for that. Oh, not this loss, this similarity measure, right? So we have now a similarity measure for the real data in the complex large space and a similarity measure for the data in the low dimensional space. Does it make sense so far? Okay, so what do we do if we have 2 distributions and we want one to look like the other? Somebody else. Yes, KL divergence. That was what you guys wanted to say, right? Exactly. KL divergence for the win. So this is exactly what we're doing. So we're basically then taking our lower dimensional representation, right, and the large dimensional one, and we kind of optimize it to match each other, right? So actually, in this case, yeah, fine. Okay. So we optimize our KL, right, and we can do this using gradient descent, and that will leave us with these kind of with these gradients, right? And they're like a bit ugly and everything, but I'm just wondering, give me 1 second. I'm missing the perplexity slide. Are you kidding me? Don't use PowerPoint. Okay, I'm gonna do this ad hoc. So perplexity is basically a measure. I'm not sure why it's not showing. Just give me 1 second. Why is it not showing? Any questions so far? Other than why does PowerPoint suck so much? Yes.
I did not get quite what similarity means. Is it like, I mean,
Yeah.
structural similarity?
No, so similarity is like, so imagine you have something very high dimensional, right? And you kind of want to project it into something lower dimensional, right? It makes sense that things that are similar in the high dimensional space also look similar in the low dimensional space, right? So that like basically you kind of want to say like you have let's say like what is the similarity between different breeds of dogs, right? So you have like maybe like small dogs, you have large dogs, and these are like dogs with short hair, dogs with long hair, these kind of things, right? So and if you like want to measure now, for instance, without explicitly saying that these are the features that you kind of want to say like, okay, hey, I look for other dogs that look like me, right? So you need a similarity measure for that. Does it make sense?
But it's case specific.
Yeah, it's per instance. So each it's not symmetric. Like each data point tells itself, like in this case, an SNE, tells itself like who are their closest neighbors, right? Like where is this? I'm so sorry about this. Give me 1 second. Where's the perplexity? What is messing with me? Okay, it doesn't matter. So perplexity is basically a 2 to the power of log of the entropy of P. I know that this doesn't help you anything if I just say it like this. That's what I wanted to show you. But one last try. You know what's called? No idea. No idea why it does that. Okay, it doesn't really matter that much. So, but basically, the idea is instead of defining sigma directly, we try to define it via a way that like refers to the number of data points that each data point wants to be similar to, right? And we refer to this as perplexity. And the perplexity, to be precise, would be 2 to the power of log h over the data point, right? Or the data distribution. And you can actually solve for this if you want to maintain this exact number, right? You can solve for this, and this will give you an exact sigma, right, for the distribution that you're looking at. Does this somewhat make sense in words? During the 5 and 5, I will find you the perplexity slides. Okay. Okay. But yeah, where were we? Okay, so we basically have now like oh, you don't see the slides. That is stupid. Good thing we did the evaluation already, huh? Prof is not prepared. Okay. So we're good. We're on track. Okay, so the similarity makes sense now in high dimensional space, right? Okay. So in the lower dimensional space, it's very similar, right? So just basically measure the similarity somehow, and we've actually, in both cases now, our similarity is a probability distribution, right? And because we have those two probability distributions and we want them to be close to each other, we basically can use like a Cal divergence in order to enforce that, right? So we optimize that. So we're looking for like those representations, right? Like those lower dimensional representations that make these Cal divergence, or that maximizes Cal divergence, right? Oh, sorry, that minimize the Cal divergence. Yeah. And we can do this like, or we can solve for the Cal divergence also through gradient descent. That leaves us with this ugly gradient over here, right? That again, you will not have to know by heart. But the idea in general is that we like basically start from like initial random null distributions throughout around the origins, and then use gradient descent with like momentum, and then add decaying Gaussian noise, which is also referred to as simulated annealing, right? So at the beginning, we're very explorative, so we jump around a lot, right? And towards the end, we basically calm down a little bit, right? So the name simulated annealing, if you've never heard of this, comes actually from, I think, metallurgy. I'm not 100% sure anymore. Yeah, so that helps in order to avoid local minima. Okay. So how can we improve SNE a bit more? So we can, instead of just using this asymmetric similarities, or the ones that are not symmetric, we can introduce symmetric similarities by just taking the non-symmetric ones, right, and symmetricizing them, right? So basically you create a mixture between those conditional ones and divide them by 2. Make sense? Okay. And like you can, and that actually has as an effect, if you go ahead and do this, that your actual gradient also simplifies, which is very, very neat, right? Because simpler gradients also like usually improve the learning problem. Okay. So questions about SNE so far?
May I ask?
As much as you want.
I have not completely understand how you defined probability distribution. You first transfer your distance between points to probability, and then you want to create some distribution to use scale divergence.
No, this is already a distribution. So this is a distribution, right? And this is the probability or the conditional probability for j given I, right? So this
point is like a center point.
Yes.
And then from every
It's a conditional distribution, right? So you have basically as many points as you have, that many conditional distributions do you have.
Mm-hmm.
Right?
That makes sense.
Excellent.
What is the benefit of centralizing our distribution?
You're centering the distribution around the point itself, right? Like so.
I meant like the last slide that you showed. I'm not sure.
Like the symmetry, right? So for one thing is that you actually, well, it simplifies the gradient, which is nice, right? But the other thing is also that you kind of, if you have this asymmetric distances, right? You always have to look. So for instance, if you minimize the distance, let's say from point I to point J, right? You're not actually sure if you also minimize the distance from J to I, right? Because it's not a proper distance measure. Mm-hmm. Whereas if it's symmetric, you know that like, okay, I touched I and J already. I don't need to touch J and I already again, right? Okay. So there's still significant problems here, right? And the most, like the biggest problem is in general the crowding problem. So this is a general issue with dimensionality reduction, right? And the idea here is that if we live in this, or if we live in this very high dimensional space, right, we have a lot of like data spread out quite well throughout the space, right? But as soon as we project it down onto the same, let's say, or like onto a smaller dimensional spot, right? These, for instance, imagine a line between my fingers, like in the center between my fingers, right? Like right now, they're fairly far away from each other. If I project them now on the line, they're very close, right? So, and if you now have a very high dimensional space, there's a lot of space to escape to, right? So like the data points can be very, very far separated from each other. But as soon as I project them on a lower dimensional space, they get crowded, right? So these global structures get destroyed, right? So there's actually this problem that like there's suddenly this overlap of these data points that like where they wouldn't overlap in a high dimensional space. So they suddenly become similar in the low dimensional one, even though they're not. Does it make sense? You agree? You look a little bit skeptical at me. So like if you disagree, feel free, right? Like I'm not infallible. So yeah. So that's a general issue, right? So for instance, like if we have something like this, right, and we want to project it now into the lower dimensional space, like ideally we still want to have something where these spots might like be close to each other, right? But these spots are not, right? well, they might still get squished together, right?
Would it also be that in the lower dimensional space, the gaps between two clusters become greater than before, or only the other direction that they might overlap?
That's a good question. So the question is if a projection to a low dimensional space could lead to greater distances. So we first have to be a bit careful what we mean with greater distances, because our overall space changes, so distances are different, right? Or mean different things now. But with that in mind, I am honestly not sure if that might occur, but I would doubt it. Like I think but it could, because there's a lot of randomness in TSNE in particular. So it might. I honestly don't know the answer to that. Good question. Okay. So how does TSNE, or like more or less how we actually deal with this crowding problem now, is where the T in the TSNE comes in, right? So we have instead of using a Gaussian, right, you can see there's very little space between, basically, if you want to maintain a certain probability still, right, like something that is not non-zero, right, there's very little space where we can go. So we need like a distribution that is so-called heavy-tailed, right? Like we need someone like a distribution where there is still a significant non-zero part or probability mass, or mass assignment further away from the point, because what that allows us to do is to spread out the data more around the low dimensional axes. Does this intuitively make sense? Right? Because if I have like these heavier tails, it's okay that the distances are larger without those data points like completely disappearing, because they get zero probability, right? Okay, so it doesn't really matter what the pseudo T distribution equation is. I just wrote it in there for your information. But in this case, the red line here would be the pseudo T distribution, and the blue one would just be an ordinary Gaussian, right? There's some nice side effects, for instance, that we don't actually have to compute any exponentials anymore. So that's really, really neat. And just for you completely to be sure, n is the only, or some other actually really cool stuff here that's not on the slides. N is the only parameter, right? If n is the only parameter, what does that mean? Which parameter disappeared? Sigma. So we don't need this perplexity and this computational cost of generating sigma from our desired perplexity, right? So that basically goes away. We don't have to do this anymore, right? Does it make sense? We use this now and like for the low dimensional space here now. So what does that mean then here in this case? So we have in our TSNE embedding now, we can actually see that this basically looks significantly nicer in terms of that there is a short distance here, but they're not directly clumped together. So if you can see the unrolling of the overall structure, right? And in this case, this would be a scenario where we can still kind of see the global structure, but that's actually one of the big problems of TSNE, that it doesn't respect the global structure as much as, for instance, UMAP does. But we will talk about this in a second, right? So also, in terms of just like evaluating the crowding problem, right? So if we use vanilla SNE, you can see like the color basically indicates how much pushing we need to do, right? In order, or like how much force we need in order to move data points closer together or further away from each other, right? And we can see that here's barely anything happening, whereas here we have like the correct forces at the correct point. So if like points are close to each other or like far away from each other in the high dimensional spaces, right? So we kind of like need to like push them closer together. And if they're too close in the high dimensional space, we kind of need to push them further away. Yeah. So I mean, again, in terms of organization, that's all neat and fine. But we can do certain things that don't actually help in terms of the computation itself, but in terms of visualization, right? So, for instance, we can do early compression, meaning that we introduce additional penalties, so just like similar to regularization, right? Into the optimization, and also like further increase large distances in mapping, like so. Yeah, adjust the distances. Yes. So in a nutshell, TSNE, or like it's T-distributed stochastic neighbor embedding, right? And how does this work? So like, first of all, it's a visualization technique, right, for high-dimensional data. It has a random initialization, which basically means that ideally or potentially you have to do multiple runs until you see something that makes sense, right? Like, or until you get like a very good visualization. And if you actually want to like incrementally add new data points, you will have unfortunately to rerun everything, right? Because this computation of your additional, like of your neighborhood and like these kind of things actually depends on all the data points. Yes, a question back there.
In general, be worse than PCA when it comes to very high dimensional data because of dimensionality?
So the question is, like for the recording, question is if a TSNE would be worse than PCA for very high dimensional data. You're referring to because we like need to compute a neighborhood now, or
in extremely high dimensional data, the volume that is contained in the shell of a high dimensional sphere is greater than the volume
that's the orange thing.
So distance becomes essentially meaningless, and PCA can still focus on certain directions, while I don't see how TSNE would do that.
Yeah, so I see what you're saying. So basically, you're arguing that like something like this will have no distance, right? Like basically would kind of lose any meaning in a high dimensional space. Yeah, I think you're correct. But I think the question now is like what the threshold would be. So how high dimensional would the space have to be for this to really become a problem, right? And I think in practice, like we're talking about like several thousands of dimensions, right? Like so, yeah. Empirically, I would still say SNE actually performs quite well, like also in high dimension spaces, right? Yeah, but I see your point, and I tend to agree there. Yes. Yeah, so there's one big downside, or not only one, but like one of the big downsides of TSNE, or generally these SNE approaches, is that in contrast to PCA, it's not reversible, right? So we're basically producing some lower dimensional representation, and we're going to look at it, right? But we cannot take this, for instance, without a lot of effort as like a, let's say, like a learning signal or something like this, right? So if we wanted to maximize our like TSNE embedding and so on, right? Like, and we want to train our actual model in order to produce a projected latent space that is very interpretable, that's not trivial to do, right? And reasons for that are, for instance, like the randomness, but also like simply the one directional optimization here that we're doing. Yeah. So yeah, and the other thing, as I already mentioned several times, is basically the like local structures are preserved very well, right? So we can see that these points all kind of belong together, right? But the global structure, not so much. So it might be that there's actually this whole cluster should be significantly further away from this cluster, right? And so on, but we don't embed this in or this is not actually considered in the visualization or like in the produced latent space. Does it make sense? Like the difference between global and local structure? Excellent. So something that tackles this, or like the new state of the art in terms of data visualization, would be UMAPs, or uniform manifold approximation and projections. Don't worry, we're not going to talk too much about Riemannian manifolds, right? Like so, but so just for me, out of curiosity, how many of you are familiar with Riemannians? Okay, cool. Maybe we should have talked about this. It's not important. It's not that important to understand UMAP as on a large scale, but think about it as a maybe I say like two sentences about this. So we are usually referring to our common space as like the Euclidean space, right? So everything here is what like usually we refer to as flat. So we have our Euclidean distance, and we can use that for like the measurements and everything, right? So, however, if we actually want to like analyze more complex spaces, right? So, for instance, spaces that have a curvature, right? The straight line might not be the shortest line anymore. So instead, we need like different measures, and those basically would be what gives rise to Riemannian geometry, right? The idea is that now, for instance, on curved spaces like circles or toruses, or like even like super like wavy manifolds, right? So we are able to measure so-called geodesics, right? Which are the straightest or the shortest line. And we often do this by approximating this, or like by doing the distance calculations on the so-called tangent space. But none of this matters for you, right? Just so that you kind of know that this is basically a more complex space than the Euclidean space. Yeah. Exactly. So like a couple of things that UMAP has going for itself, it actually it presents a bit more formalized TSNE approach, right? And it actually has this ability, and we will see this more closely afterwards in a short demo, to actually preserve like global structures better, right? Like, which is exactly what we want from it. So how do we actually get from TSNE to UMAP? In general, Peter, leave the people alone. This will be so weird when we're recording. Anyway, we just cut it out.
Kannst du nehmen?
So,
Kannst du nehmen, welcher Allergie?
Oh, yeah,
so
exactly.
Peter, geh. Das weiß Peter. Okay. So we basically like in general talk when we talk about like structures. So just go. We have to cut it out now. Like Peter, geh. Okay. So in general, when we talk about like these graph-based dimensional interaction approaches, there's like always two steps, right? So there's the graph construction step, where we basically build up our graph, and then there's the graph layout step, right? Where we then try to basically map these graphs to each other, or the one to the other one, right? So and in TSNE, as we've seen, we kind of have like this Gaussian probability for like the distance measure that we use for building up the graph, right? And then we deal with the asymmetry through this kind of like averaging, right? Or this like this basically adding itself and then dividing by 2n, right? And as a kind of like as an objective to match those to each other, we use the Cal divergence, which is fine. And we can mathematically optimize this whole thing through gradient descent, right? So now the question is like if we can actually adapt the steps to get like better performance out of it, right? So let's talk about the graph construction for a second. So again, this is like a lot at the same time, but let's go through it step by step, right? So in order to construct a graph, we need two things, right? We need to have sigma I in this case here, right? For like this value, like or you can assume this value over here, and we need rho I. Rho I basically just tells you the closest distance that you have to any other like data point, right? So not to yourself, obviously, because that will be zero and that will be boring, but to any other data point, right? What is the closest distance? That's your rho I, right? And then in order to get sigma I, we basically need to, again, this shouldn't be fair. We kind of need to optimize it similar as we would have done with the perplexity step, where we basically say like, okay, we kind of want to make sure that the left-hand term, right, always sums up to log 2 of k, and k is the number of desired neighbors that we want to consider in our similarity measure. Does this make sense so far? Right? Okay. So how do we actually, and what is inside of our term? Again, this looks very much like a Gaussian. It's not quite. It's just like an exponential, but you can imagine that this is like similar to a ReLU, right? So we basically take the maximum between 0 or whatever the distance is, right? And we look here for every point, right? And measure and take the difference between a closest point and every other point, right? That's what we look here. And we want to find so if we actually consider this part, then this would correspond, or like, oh, you can also look at this. Like if like this part, this would correspond to some weighting term. And basically, because we are sure that this is supposed to be the same as log 2k, right? That gives us everything we need to compute sigma I, right? Because sigma I in this case here would be the only unknown, right? So we can establish the whole equation and so on, such that we get sigma I. Yeah. So what this then looks like is if I have k neighbors, right? So because the negative in the exponential, we kind of have like this smooth curve going down where we have like an exponentially decaying distance to the k next neighbors, right? So my closest neighbor will get value 1, and then the next one will get, depending on their distance, the value 0, and then depending on the distance, they will get more and more exponentially decaying weights for that. So does this make sense how we now compute sigma I, right? So the hyperparameter that we set here is k in this case, right? So we want to consider k neighbors. Make sense? Okay. So with this now, so we have now all of our w's, and we basically can make sure, guarantee that there will be between 0 and 1, right? So we can now create what is called a fuzzy set. Like, just very quick, who knows what a fuzzy set is? Okay, so like usually when you have a set, right, you have a set of elements, right? With a fuzzy set is you introduce an additional weighting term that tells you how sure you are that this element belongs into the set, right? That's a fuzzy set. So we have basically our elements, F, and we have a weighting, or like the fuzzy weight, that is somewhere between 0 and 1, and tells me like, oh, I'm pretty sure that this is part of my set or not, right?
Is there a limit to the evaluation of the F? So, for example, if you would sum up all of the weights for one set, is there an upper limit? Except for the size of the set times 1 times.
It should. I mean, the upper limit in this case, if you sum up all of if you combine the weights, given I for all the other j's, that should always be limited by log 2k.
Okay.
Right? Okay. Yeah. So of course, like that thing is now still not symmetric, and as we seen before in TSNE, we want to have like something symmetric, right? So here the idea is what we do is we use the so-called T conorm, but in general, it's really like, I mean, this would be element-wise, and this is what would be the equivalency that we take. Like we have our adjacency matrix, if you want, right? And that one is not really correlated. I don't know why it's like this. Okay, so that one is not really correlated. Not correlated. Sorry, that one is not symmetric, right? But we can symmetricize it by just adding the transpose to it, which will automatically make it symmetric, right? But in addition, we also subtract the square, or like not quite the square, but like the square transpose to it, subtract from it, right? And that gives us a symmetricized matrix B that we can now use for the actual fuzzy weights, right? So now we can have the benefit that we, in the optimization steps, don't have to look at, like in terms of practicality, at all the data points. You seem unhappy with it? Yes, no? No?
It's just a lot.
In general? Okay. What is my time actually? Okay. So where did I lose you? When I showed Super Mario, right? Like that was
Pretty much the next slide. Like,
this part.
This one.
Okay. Again, so okay, so in this case, what we want, right? Similar to before, we had this this probability, which basically constituted like an assignment, right? Like a distance assignment to each point. Like each point, xi, like for each point, we knew that like the other k points had this distance to myself, right? So if I would be I, we kind of want to have something similar again, right? We want to have the same thing again. So, but the way that we compute it in this case is slightly different, right? So, what we want to show this slide. What we want to end up with would be these ones, and those would be the analogy to P of j given I, right? Those would be these weights, right? The non-symmetric ones yet for now. But in order to compute them, right, we kind of want to structure, or like we hand define a structure like that we compute these weights like this, right? And for this thing to be computed, we need rho I and sigma I, right? Rho I we just define as the shortest non-identical point, right? So the point that is not myself, but the shortest one. So those are the distances. And that will help us in this entire thing to make it relative to this point, right? So if, for instance, like I have, like if my closest point is very far away, right? Then like the one afterwards will not be again very far away, but it will be like a little bit further away than the previous was. Does it make sense? And that's kind of what we do here. So we say like, okay, every other point, right? How much further away is it than the closest point? Make sense? Okay. And now basically we kind of still want to define a spread around this, right? Which is where the sigma comes in. And for the sigma, in order to solve for the sigma, we basically define, okay, the sigma, again, gives you kind of like an area and spread, right? So alternatively to defining the spread, we say we want to include k neighbors, right? So we basically say like whatever our overall inclusion should be for this one data point, right? Should be roughly log 2k. So with this now, we can basically, afterwards, we don't do this here, right? But with this, we could feel like, not theoretically, but very practically, can compute now sigma j in this case. Make sense? So is that better now?
Yeah.
Okay, excellent. Or you're just saying it so I move on?
No,
Okay.
It's like
I have another question for the next slide. Maybe it's the next one. Yeah. So where we do this. Yeah.
Yes.
Maybe it's just the next slide, but I'm not entirely like if you just take A and add A transpose, and I'm not sure what the minus A times AT does. Like, okay, if we just do A plus AT, we just lose information, right? I'm not sure, like, is that A and what does that B? Like, what are the...
Okay, A is basically, imagine we have all of our weights, right?
Yeah,
so this is
the
like
weights
our
from the last,
adjacency matrix, right?
Yeah.
And then basically, but now, for instance, A(n)(0) and A(0)n are not equal, not necessarily, right?
Okay.
But we want them to be equal.
Okay.
So we need to symmetrize
Yeah.
this whole thing. And this is just one way of making it symmetrical that the UMAP people decided for, right? Okay. So, okay, and we do this, again, we can define like our weights like this, the symmetric weights now like this for the high dimensional space and for the low dimensional space, right? And then with this, we actually now kind of want to like get them close to each other, right? And we can do this by optimizing the so-called fuzzy set cross entropy. And if you look at this closely, right, you should see that it basically resembles again a KL divergence, right? So that thing pops up everywhere, right? But in addition, we have like a so-called non-membership term, right? So this one again takes care of the local scope, right? Like of the locality of like the local structure. And this one makes sure that there is global structure, right? Because it says like the ones that are away should stay away, right? And the ones that are here, like should stay here. Don't take this out of context, right? So, but like this is basically for the data points, like yeah, so that's great. So reinforcing gaps. So if we again, those equations don't matter for you in terms of examination, but I think it's still worth seeing them, right? What those are, if we actually just take the gradients of this fuzzy set cross entropy, we actually end up with two terms in there, right? Which are something like attraction and repulsion forces, right? So basically, similar data points get like assigned like closer to each other in our low dimensional space, and points that are different or separated in the high dimensional space get pushed away in the low dimensional space. So yeah. So what do we do then in terms of practicality and implementing it? So we initialize. So this is one of the steps that they're doing in order to make it more repeatable, right? We're initializing our points now using something called spectral embedding. Doesn't really matter what it is in the context of this lecture, right? But then we attract all our neighbors, right? Like, so basically we do the attraction to the neighbors, but repulse a random distant node. So we don't repulse all the distant nodes, but at any step, we just pick one random distant node and put that one away. And why we do this is because, like, yes, we might need more steps in order to push all the global structures away, right? But look, we still overall, once we run enough, we've randomly pushed everyone away, and because we have a symmetrical distance now, the distant one also will have pushed me away at some point. Does it make sense? And because also, maybe it also pushed away one of my neighbors, but because of the attracting part, I'm pulled closer to the neighbor at some point also. Does it make sense? Okay. So with this, we're basically done, right? So my clock says exactly 30 minutes. Right, so the UMAP TSNE basically has a couple of parameters which are more intuitive than the TSNE parameters. So for instance, we have the perplexity parameter for TSNE that you unfortunately haven't seen, but in UMAP that would literally just be the number of neighbors, right? We have like the number of epochs that we want to do to optimize this. And we have like a deterministic initialization instead of like a random initialization compared to SNE. And that actually leaves us with like beautiful, beautiful low-dimensional representations, right? And you can see here again, local structure preserved, even here to a certain degree, but not quite, right? But here we also have the global structure preserved, right? So like clusters that are closer to each other in the real data, also closer to each other in the other data. Mm-hmm.
Maybe I've missed it, but how exactly do Riemann manifolds come into play?
It's because like the whole definition here, basically the distances that we defined would be the ones that would be the measurements or the shortest distance in a Riemannian manifold. But it doesn't really, like, again, don't really worry about it. I mean, we can talk about this offline, but in terms for everybody who just cares about knowing this kind of thing, for the exam, we will not ask about this, right? Because we haven't introduced Riemannians and so on. Okay. Yeah. So with this, I just wanted to show you this really, really cool website that the guys from Google did. Minimize this, maximize that. So I think we have the link in the exercises, but like, so this would be, for instance, some of the visualizations that you would get for UMAP, right? And you also have comparisons to TSNE, right? So again, here UMAP, global structures, nice. TSNE all clustered, right? And this is for, I think, fashion gymnast in this case. We can see this. There's like some more stuff down here, which is really neat. So for instance, you have the original data, which looks like a mammoth, which is great, right? And you can actually, and this is the beautiful thing, you can play around with it and undo it again, right? So because like this, so like if you only consider very, very few neighbors, then your local representation will suffer, obviously, right? But then like the more neighbors you have, right, and distances will affect your local and your global representation. But you can see, like, even interpretable, like those still look like the mammoth, what do you call them? Tusks. Thank you. And yeah, and if we would compare this, for instance, to TSNE, right? Again, like on 2 dimensions, I would argue that this would still be more interpretable, right? So a big issue with UMAP still, or a issue with UMAP still, is that similar to SNE or TSNE, you have the issue that like it's one directional. So you actually, like there are some approaches that try to make it bidirectional and then like leverage this for learning, right? But in practice, like in general, it's a one directional path, right? So you can analyze whatever you've seen, but you cannot actually leverage that to improve like your learning itself.
What about new data points? Would you also have to update the whole UMAP?
That's a very good question. You might have to. I have to look this up again because I don't know necessarily if you have to, but I would assume you kind of do because you're also limited to the k nearest neighbors. So a new data point would basically affect this neighbor assignment. The question is, what I'm not sure about is how robust it would be against it. So like if this new neighbor would destroy the entire thing or if it would still be like preserved somewhat, right? But it's a very good question. Okay. Let's do, if there's no other questions, let's do a 5 and 5.